chapter 16, slides 1 through 7. This chapter, for the most part, is a review, and we're going to be talking about resonance. The term that I'm going to introduce to this chapter is called conjugation. And so what you're going to see is conjugated pi systems is just a definition of the relationship when you have resonance. So I could say something, let me just use it in a sentence so you can get an idea. These two pi bonds are conjugated. They can resonate, or resonance can occur among these pi bonds. Why? Because they're conjugated. These pi bonds are not conjugated, thus they cannot participate in resonance. So do you see how I'm using the word conjugated in the sentence? Basically, when you have the ability to resonate pi electrons, the system is said to be conjugated, related to each other, right? In sync with one another, or in a relationship such that resonance can occur. So it's a new term that we're introducing, but it's not a new concept, right? You guys have been talking about and recognizing resonance for a while now. So there's really no fundamental understanding here that's new, just a new term. Let's recall SN1 and E1 solvolysis. We're going to just take some of the stuff now that we've studied relative to chemistry, to the reactions, and apply it to conjugated pi systems. So SN1 and E1 solvolysis, right? The leaving group leaves. And what you can see here is that we've got a leaving group, chlorine. And although it is primary in both cases, A and B, which one will undergo solvolysis more rapidly? A or B? Which one will undergo solvolysis more rapidly? Well, if you guessed A, you'd be correct. And the reason being is that primary leaving groups, when they leave, you end with a primary carbocation. However, in A, it's primary, but it has resonance stability. So this carbocation is said to be conjugated with the pi system. Okay, resonance can occur. Thus, the carbocation is conjugated to the pi system. It's like saying it's related to or can interact with. Okay, so you would say the answer is A, because the resulting carbocation is conjugated. So I use the word conjugation in a sentence. Okay, how about another system? How about the following? Which would undergo a faster radical reaction? So this is if we had, say, like a bromine radical and a bromine radical, this would form a bond to form HBr, and you'd end with a carbon radical. So what you're doing, and again, you never make hydrogen radicals. We would make HBr in both of these cases. So what we're doing is we're comparing this right here. And this is a tough case. I would say that these are pretty much the same, right? This is a tough call. About the same. Why? Because although the top case, A, is primary, it has resonance. Primary radical is conjugated. It has resonance. while the bottom is stabilized by induction, it's tertiary. So here you can see that although they are very different, and you'd probably think, oh, tertiary, you can't discount the fact that the primary one has resonance stability and is conjugated with the pi system next door. So this is a tough call. What about an acid-base scenario? If I applied acid-base chemistry to each of these, okay, so the base removes the hydrogen and leaves a negative charge behind. You're evaluating the negative charge or the conjugate base left behind, and you're going to use REO. Of these two anions or conjugate bases, they're both carbons, so the atom doesn't really help me. Then you go to resonance, and you realize, oh wait, they're both primary, but the top one has resonance stability. Therefore, the anion formed in A is conjugated and has resonance stability. So therefore, of these two, I would assume that A is the better acid. So again, this is just showing you we've already done this stuff. The only thing I'm doing is using the word conjugated in the sentence, saying that to sort of define the relationship of either the pi system or the charge, the radical, the carbocation, or the anion. If there's no resonance, then the systems must not be conjugated, must not be related to each other. So conjugated pi systems, how can we explain this? I've summed up what we just looked at down below. You can see that there's a radical, carbocation, and anion, and they're all conjugated systems. And what this means is when your charge is in a position allylic to the pi system, it is said to be conjugated. It can resonate. So we have all of these terms, right? But really it's the same concept that we've been talking about. We bring this up because of the next chapter. The next chapter is really going to focus on the understanding of resonance and the effects of conjugation. So we're bringing this up again just to bring it back to the forefront, introduce this new term conjugation, but also take a look at the effects that resonance and conjugated pi systems have on certain reactions or on old reactions that we've taken a look at before. Remember that the top answers in organic chemistry are typically steric hindrance issues, induction or electronic effects, and resonance, conjugation. So allylic carbons are just really a fancy term for the next carbon to a pi bond. And so when you have a charge at this position, it's said to be conjugated. Okay, kind of repetitive, nothing new here. That's why I had the big green review sign up at the top. The only new thing to this section is one unique reaction. And this is exploiting the fact that we can very selectively hone in on the allylic position. Okay, so what I just showed you here, I want you to focus on this reaction right down here. I showed you that the allylic position, forming a radical at that position, is much more stable than just willy-nilly forming a radical on an alkyl system that has no conjugation. So we're going to exploit this stability to do a very selective reaction. This is called the NBS reaction, and I've drawn NBS down below here. NBS, let's see, did I write it down? No. NBS stands for N, meaning nitrogen, bromo, this guy right here is this guy right here. That is NBS. And it's a solid, And it actually comes in the bottle with a trace amount of HBr. You don't usually even need to add any yourself. There's just a slight amount, trace amount of HBr in the bottle when you buy it typically. Now, what is so special about this reaction? Well, this reagent, when you put it into a solvent, will form in very, very, very small quantities Br2. Okay? And when Br2 is exposed to light, so go down here, we know what happens when Br2 is exposed to light, right? Light hits it, the Br2 splits into radicals, and you end up with 2 bromine radicals, and you can do radical reactions. Okay, so then you might be wondering, well, what the heck? Why do I even need to start with NBS? Why don't I just add Br2 and add light? Okay, well, the problem is that I want you to recall the old reaction. Way back, the first reaction you guys learned was Br2 and light, and we just used like propane, and we got 2-bromopropane. Notice that we didn't have any double bonds. And then later on, we looked at what happens when you add Br2 to double bonds. You form the brominium bridge, and then the brominium bridge opens up, and you get anti-addition across the pi bond. Okay? So now what we're going to do is it's like we're combining these two reactions to get a new reaction. We don't want to dibrominate, and we don't want the crazy, selectivity problems that you get with brominating a propane or any alkane. I mean, you're hoping for selectivity, but if you started with something really big, I mean, which site are you going to brominate? Probably all of them, except for the ends, right? Because they'll all be secondary. So we have selectivity issues in bromination of a propane, and we have dibromo issues when you have a double bond present. So NBS, this is the key right here. NBS allows us to generate an extremely small quantity of Br2 in solution, so that Br2 that's generated, boom, right then and there, hits light and forms your Br radicals. So there's no extra Br2 floating around at any given moment. The one Br2 that's shot off is the Br2 that gets hit with light, and there's only these 2 Br radicals floating around. There's no Br2 floating around, okay? So therefore, if you were to introduce a system that had a pi bond, the hydrogen that's the most susceptible to being abstracted by the bromine radical is the one at the allylic position because of its stability. So all the other positions are pretty much safe. So the HBr is formed, and your allylic radical is generated. Why? Because that allylic radical is the most stable. Okay, and then look, HBr was the byproduct. HBr is necessary to collapse the NBS into Br2 and the succinimide. How does that happen? Well, acid-base chemistry. So there's your acid-base chemistry. The nitrogen grabs the proton, kicking off the Br minus. This is the trace amount of HBr. And the Br minus then does an SN2 with the Br, giving the electrons back to the nitrogen. So therefore you get Br2 and the succinimide. Now, if this only happens once, and that one Br2 hits light and becomes your radical, and your radical abstracts the allylic proton, giving you the radical that is conjugated, you've just generated a little bit more HBr so that it can go back and find another NBS molecule to release a little bit more Br2. So the HBr is the byproduct is actually what helps the cycle keep going around, because it expended its one HBr to form its one Br2. No more HBr, no more Br2. Until the reaction occurs, now you've generated a little bit more HBr, can go back to the beginning, react with another NBS, releasing a little bit more Br2. We need that little amount of Br2 to continue the reaction. And this is how we put the bromine on. And we end with the product, bromination at the allylic position, and a little bit of Br radical to go back and interact with another allylic carbon. So NBS reactions are really slick because you can have a molecule that has lots of alkyl centers with hydrogens off of them, but it's the allylic positions that you're going to selectively brominate. Now let's work out one of these just to understand a little bit more about this bromination and all of the considerations. NBS, if you just think about it, is our Br radical. I can shortcut it and say, yep, it generates Br2 with a trace amount of HBr, and then with light, it forms two equivalents of the Br radical. And I always think of it, if you've ever had like a pill and it's in a slow release capsule, right? Because it's gonna dispense the medicine in your stomach very slowly, right? It's like, I always think of NBS as the slow dispenser of Br2. We don't want tons of Br2 floating around. Why? Because we don't want this reaction to happen. We don't want to add two Brs across the double bond. We want the double bond to stay, and we want to brominate at the allylic position. So we can't have an enormous amount of Br2 floating around. That's why we have to use this special reagent, a slow release of Br2, so it gets kind of used up very quickly. So NBS is just our Br radical source that releases Br2 very slowly. We identify the allylic position. So here is my allylic carbon with a hydrogen off of it. This is going to form a bond. I'm going to form HBr and an allylic radical. Now, what you need to do is you need to consider resonance. Because this radical was formed, I do know that yes, it could react with another Br2 and give me a product. But would you not agree that this radical is in resonance because it's conjugated? And because it's in resonance, this radical also exists. And because it's in resonance, one, two, three, four, five, 1, 2, 3, 4, 5, this radical also exists. Remember back from your homework that cis-trans isomers, when you open it up with a charge next door, resonance allows rotation because the double bond is not locked and set. So I've actually got one possible product. If I brominate here, I get a second possible product. And if I brominate here, I get a third possible product. Okay, so 1, 2, and 3. Which is going to be the major product? Well, in these cases, we can actually employ Zaitsev's rule and understand that we want to minimize steric hindrance. And Zaitsev's rule says that the more substituted the double bond is, the more stable the compound, the more thermodynamic, as found from hydrogenation studies. So I would suspect that this compound is the major product. I'm going to leave this last one for you so that you can determine all possible products and which product is the major product for this second example.